review, but we'll have basically the curriculum completed by April 7th, the first Wednesday in April.
Yeah, but that's great. I think I said in the session this morning that we had made the adjustments.
Okay.
For persons who are following the tutorial program, we want you to do the revision program on the 14th. So we're going to press ahead with it.
Nice.
And we'll schedule the exam from the window between the 16th and the 19th.
Perfect.
All
okay.
Right.
And I'll PDF the presentation again and send it to you with the answers from last week and the questions. So they'll have all of that. So that, you know, by the end of the session, they'll, the students will have a good collection of information to draw from. And really the review session, the way I've done them is, we'll focus what we think the exam, you know, will emphasize.
Absolutely.
Okay.
Well, once you send them, we will circulate promptly.
Right. No, that's great. I noticed. I tried again, and it's interesting. This Zoom doesn't let me send files from my computer.
I don't understand. I must check it out in the background because it should actually. I suspect maybe because you are.
It's only letting me do it from Dropbox or SharePoint, but you know, I've got them right on my hard drive. Normally it shows up computer, and then I can just click on the file.
It's supposed to allow you to share documents and links, etc.
Anyway, hopefully it's not too much of a pain, but I'll send them to you directly after the session, so you can circulate.
Okay.
Cool. All right.
Well, get rolling.
All right. Well, let's, as they say in the prairies in Canada, pitter patter, quit the chatter, let's get at her. All right. I was going to say good morning. Good afternoon, everyone. I will share with you the PowerPoint that we're going to look at today, and a couple of videos as well. But I thought we would focus today on valves and hydrants. There's quite a few questions on both level 1 and level 2 on valves and hydrants. So I wanted to cover that off. All right, just have to close the door. So as I mentioned in a previous session, you know, a lot of the certification exams, as you know, if those of you that have taken them, you call them refrigerator theory. You need to have this information in the refrigerator that is your brain. And then when you open the fridge at exam time, hopefully everything's still fresh and hasn't turned like 3-week-old lettuce and carrots. So it's still good and you can get the right answers on the test. So that's really what we're looking at. So today, following that theory of refrigerator theory, we'll talk about the need to know valves and hydrants for both level 1 and level 2 exams. And we'll focus really on, for operators, it's recognizing the type of valve and then pairing up the valve or hydrant with its correct usage. And we'll talk a little bit in the operations and maintenance sections to follow, you know, how hydrants, for instance, are used when we do water main flushing, and what an inspection of a hydrant really details. Which valves and how do we maintain and exercise valves to ensure that when we need them, they work correctly. So today's 2 hours. Again, we'll get you out of here by 5 o'clock your time, slightly before. We're going to talk about the types of valves used in water systems and why we have such a huge array. I mean, there are a lot of different valves that you've probably come into contact with or will in your water system careers. And, you know, just in 25 words or less, basically mechanical devices that we use to stop, start, or importantly, regulate water flow. The ability to, say, manage water pressure from a higher elevation area to a lower elevation area without blowing the water system up. And to do that without having an operator stand by to do that manually is tremendous. And so we have a certain type of valve to do that. We also have valves that when we need to release air from the system, it needs to work without an operator there. Or to stop water from flowing in an unintended or opposite direction. And so we use check valves for that. So we'll go through the types of valves in a water system. And again, for those of you writing exams, we'll match up the valve with the type of question that will be asked on the exam, so that obviously not just that you know the answer, you get it right. All right, so again, for a water system, and think of your own water system, the manufacturers will change, you know, from region to region. In North America, the American Water Works Association does have standards. And I hope you get a chance, if you've got an internet connection, to go to awwa.org to look at some of the resources they have. They provide the organization and the regional subsidiaries, BC, Alberta, even California or Mexico or Caribbean. They have lots of supporting resources around all aspects of a water system. And valves are a critical part. So what do we use valves for in a water system? Well, sure, we use them to isolate a section of water main. So you'll see in the intersection, you know, you'll have to control a valve, shut a valve, isolate a section of water main between two blocks or half blocks, depending on density. But when we do that, we're dropping the grade line, right? We're knocking the pressure down so that we can either do some work on the valve or on the main or on the valve, or make a repair or do a tie-in. We have various reasons, legitimate, good reasons for isolating a section of water main or a series of water main, or isolating a meter or a tank to do work on it. So we have certain types of valves that do that. We need to drain a system. We have a valve for that. If we are flushing and we don't have a fire hydrant, we might have a blow off at the end of a section of dead end main in order to preserve water quality. We also have the ability to throttle, and throttle means we're not going to close the vein all the way down, right? The valve is going to remain partially open. Well, from our hydraulics, we know that when we change the cross-sectional area across a pipe by starting to close a valve, water tends to speed up and we get a pressure drop. And if you stood on the road or on the sidewalk where you have a valve and you have to isolate it because of a water main break, you can actually feel all of that turbulence as the velocity changes because you're slowly closing the valve. Well, if you don't close it all the way and it remains throttled, okay, we have reasons for doing that. It may seem like we don't, but you know, you may be assigned to actually do that to prevent excess flow from moving from one area to the other. One of the most important areas of water valve usage is around controlling filling and emptying of reservoirs, whether they're above ground, below ground, whether they're 1 million gallons, 10 million liters, or 50 liters. We need to regulate that. And again, the goal is to do that remotely. So if we can do that without having an operator have to dispatch someone to open up a valve, close it, and then return afterwards to open it up again, that gets very expensive. In fact, I know that because in my first years in North Vancouver, I was 18 years old, and we had 2 reservoirs filled, and they were different pressure zones. But the one reservoir pumped to the higher reservoir. In the summertime, it couldn't do both. It couldn't supply the neighbors and pump up to the next reservoir. So because they didn't have a way of communicating at that time between the 2 reservoirs, they sent students up there at night between 8 p.m. and midnight to manually open the valve to allow the reservoir to pump up to the next reservoir. But that meant that then the one reservoir started to drain too quickly, so then you had to watch it, shut it. When it started to fill up past a certain mark on the tank, on the outside of the tank, you could open it and let the other reservoir fill. So we were juggling how to fill major neighborhoods in North Vancouver at the time because the system couldn't do it automatically. Well, control valves do that now. And that's good because it's terribly expensive to and unreliable to have an actual operator do that. And lots of room for error. Another reason for using valves is to control water hammer. And when we talked hydraulics, we know that, you know, stopping water flow suddenly, either because there's been a power failure or someone's operated a valve or a hydrant too quickly, can send this pressure wave back and forth, right? Water doesn't compress, so that pressure has to go somewhere, and this wave moves back through the system and can actually create more breaks, bursts, and or damage to fittings. Well, we need to take that extra energy away in the case, say, a pump fails or there's a power failure and the pump shuts off in mid-cycle. So we control that water hammer remotely, and we'll show you valves that do that. Bleeding off air, so that, you know, air tends to collect in water mains, either based on temperature changes in the water, treatment processes, breaks, leaks, back siphonage. So how do we get rid of that air and at the same time not allow a vacuum to occur? So we install air valves, air release valves, most of them double acting, and we'll show you how, just to prevent that. And of course, you know, when we sell water, provide water to our customers, typically through a water meter and the connection at the property line or in the house or building or retail, industry, etc., we don't want that water coming back to the municipality, ever. So we need to prevent backflow. And so we've got some valves that are set up specifically for that purpose. So we'll go through each of those. Basically, though, the real key valve that we use in a water system is a gate valve. We isolate the water main from one section to another. And there's a couple of bullets there. Why? Well, we need to, if there's a water main burst, or if we have to tie in a new water main, or if we're doing unidirectional flushing, and which is a maintenance activity that also relies on changing the direction of the flow in the water system. So we need to isolate valves for that. On a smaller scale, every individual service connection to a home or a business may need to be isolated from time to time. And when we say isolate, we're talking about from full flow, full open to full closed. And those kind of valves that we typically use for that are gate valves, right? We can drain the water line with a blow-off valve as well. Typically, we use gate valves for that purpose. We'll talk some more about altitude valves for throttling and regulating. But let me stop this. Let's go through. I've got a video that I want to set up here on the types of valves that you'll recognize. And I may stop the video in a couple of places just to highlight some things that may be on the exam.
The valves used in a water distribution system generally fall into one of the following categories. They're gate valves, they're globe valves, needle valves, pressure relief valves, air and vacuum relief valves, diaphragm valves, pinch valves, rotary valves, butterfly valves, or check valves. The gate valve is the most commonly used valve in water distribution systems. They are designed to start and stop flow, and they're not used to throttle flow. The disc is raised into the bonnet, and there's minimal head loss when the valve is open.
So the two keys for a gate valve are one for isolation. The exam sometimes asks which valve should not be used to throttle the flow. They can ask it the opposite way and say which valve is the best to use to throttle the flow. Gate valves are not, they can and have been used to throttle, but they're not designed to be throttled. They're really designed, and you can see in the cutaway here, they're designed to be fully open or fully closed. And when they are fully open, the gate, which is the black rubber encapsulated disc or wedge, there's certain styles, is raised up into the bonnet, so it's completely out of the flow. So a fully open gate valve also has, you know, the benefit of very minimal head loss, right? We don't lose energy through an open valve, right? Because that hydraulic energy that we have paid money to either pump up to an elevated tank or just in an inline booster, why would we sacrifice it by pushing water through half open valves? So they're designed for minimal head loss, fully open or fully closed, and again, to isolate versus throttle.
Gate valves have equalizing lines or bypass valves for use prior to opening.
So a bypass line is not shown here. I'll show you a picture in a minute. You may have seen on, and typically the American Water Works Association says that a bypass valve and line will be installed once you hit 400, 16 inch diameter or more. And you can see why just in this schematic. If I close this valve, so it shows a fully closed valve, and I have now full line pressure on this side of the valve and 0 on the other, all of that pressure is acting on this valve. And remember, the cross-sectional area, as the pipe diameter increases, that say 100 psi, 690 kPa, is acting on every square inch of that valve. So on a 6-inch or a 150 valve, that may be 200 pounds of thrust, which is totally acceptable for this stem to operate against. But on a 16-inch valve, that might be 3,000, and that stem will break. And if you've tried to operate a closed valve that has unequal head pressure on one side versus the other, say exactly, you know, when we isolate, we have full line pressure on one side and 0 on the other, you will damage that valve. So the bypass is a much smaller diameter and basically tapped in upstream and downstream, and it goes around, it bypasses the wedge and are built into the valve itself, so that when you need to reopen the valve, the bypass line is reopened. Let me just show you a picture of that. We will go to Google, because that might be the easiest way to do that. And show you what a bypass line looks like on a large water main. Let's see if we can find a bypass. I've got Google Images up here, and I just want to find a big valve that's got the bypass on it. Finding all sorts of stuff I don't want to see. We'll go by size. Well, best intentions, I will have to look for it, but I have a couple of other drawings here that show the gate valve, so we will share that with you. So what we're looking at here is a cutaway of a 10-inch gate valve, and you can see in this case, this cutaway with the wedge valve. A bypass simply sits on either side of the valve, as I was describing, so that it allows the operator to equalize the pressure on both sides without damaging the valve itself. There we go. There's a bypass, finally. So you can see that this valve would be much easier to turn, and the tap is on the upstream and downstream side of the gate. So with this valve being closed, we can now open this valve, bypass the flow, and then as soon as the water pressure is the same on both sides, the valve is easy to turn. You don't damage the valve, and you don't hurt yourself either, and injure yourself trying to operate a valve that is well beyond capability of an operator. There's another example of the bypass here. So typically 2 to 3, even 4-inch bypass, and they can be handled either with the outside stem and yoke wheel valve, wheel handle, or an operating nut, as is you know, on this example here, the operating nut, standard operating nut, and then they can be buried directly. Okay, let's do the video a little bit more. Okay.
So that the gate is not damaged. There are many different types of gate valves, including the rising stem, the non-rising stem, the horizontal gate valve, the resilient wedge gate valve, tapping valves, cutting in valves, and inserting valves, along with slide valves. So all of these different types of valves are considered gate valves.
You may be asked on the exam about a non-rising stem, or the actual classification is NRS. And that is the type of valve that can be buried in the ground, as opposed to a rising stem, or OS&Y. An OS&Y would typically be in a pump station or a meter chamber, somewhere that's not buried directly in the ground. Why? Because as you operate the wheel valve on the top, pictured here, as the valve rises inside the body of the gate, so does the stem. So the stem rises and actually rises through the wheel valve, and so it acts as a position indicator. So you can actually see the position of the valve. Is it open? Is it closed? Wouldn't work very well if you had to bury that. So the non-rising stem is typically with the 50 millimeter 2-inch square operating nut, so that you can turn the valve open or closed. And of course, it's not the stem that rises, it's the gate inside the valve. And that's a non-rising stem. So same application, isolation, but it doesn't rise, so that you can actually put a standpipe over it, bury it, which means that, of course, when you're looking into the standpipe, the valve box, you don't know it's open. You actually have to test it by putting a valve key and operating the operating nut. So be aware of the term non-rising stem.
Globe valves are a different type of valve, and household faucets are typically globe valves. Globe valves are not well suited for distribution system mains because of the high head loss within the globe valve.
So they have, this is on the exam, a globe valve, a globe style valve is typically based on not its function, but its construction, right? The style of construction. I'll show you a cutaway in a minute. And we use them all the time in the distribution system. However, and we use them because of their high head loss. We don't use them in, you know, block to block to block of a water system, because they're not good for isolation. They're really good for throttling and controlling flow. And that, we rely on the head loss for that.
They're used where head loss is not a concern, but they can be used to throttle flow and control downstream pressure in high pressure, high flow situations. Needle valves are similar to globe valves in their design. A main difference is the seating surfaces. A relatively long tapered metal shaft fits into a tapered seat, and this allows slight changes in the allowable flow area as the valve is opened. These valves are used for precise throttling applications such as hydraulic valve actuator lines. Pressure relief valves are also designed much like globe valves. The main difference is that the disc is held against the seat by spring pressure. The spring can be adjusted to lift at a certain pressure, which will reduce the system pressure. Once the pressure is reduced, spring tension will overcome system pressure and close the valve. Another variation of the globe valve design is the diaphragm valve. System pressure exerts a force on a diaphragm and assists in closing the valve. The altitude valve is the most commonly used type of diaphragm valve. Pinch valves are operated by pinching shut a flexible interior liner. These valves are limited in their use and are only available in relatively small sizes. Pinch valves are used for throttling corrosive liquids or liquids that might clog other types of throttling valves.
So very common in the wastewater side.
Plug valves and ball valves are the two main types of rotary valves used in water systems. Both valves require only 1/4 turn to fully open or fully close the valve. Small plug valves are used as curb stops and corporation stops. Large plug valves are used in high-pressure applications such as high-lift pump discharges. Plug valves can be used to throttle flow without causing valve damage. Ball valves are very similar to plug valves, except the seating element is a sphere rather than a plug. Both ball and plug valves are used as service connection isolation valves.
And that is typically an exam question, the style of valve used as a service connection, either the main corporation stop or the curb stop, are typically, and they'll give you a choice of either ball or plug valves. And of course, over time in the industry, we've gone from basically plug or cone valves, which is the shape of this, the seat and the orifice on the valve, to full port ball valves, so that now when that valve is open, it's fully open, like a gate valve, full port. And when it's closed, it's still a 1/4 turn to shut off the valve with a key or a gate valve style.
A butterfly valve has a disc that rotates on a shaft within the valve body. When it is fully open, the disc is parallel to the axis of the pipe with water flowing on both sides of the disc. Although the head loss is higher than that of a gate valve, it is more easily opened against pressure since the force on the disc is equalized. A butterfly valve may be used for throttling under low flow and low pressure conditions, but this is not its primary function.
This valve as well, because it sits in the actual flow, so it has higher head loss than a gate valve, but you'll see them quite often used as control valves for pumps because they can be actuated, controlled through the stem to throttle, to regulate, to open after a pump starts. They also require a bypass because of that unequal distribution of pressure when they're fully closed. You will see that similar bypass arrangement on a butterfly valve, so that, again, the stem is actually thinner than that on a gate valve, and so that it doesn't damage the valve itself.
Check valves are designed to only allow flow in one direction. They're commonly used to prevent backflow through idle pumps, and they're also used to maintain prime on centrifugal pumps by keeping water from draining out of the pump casing and uncovering the impeller.
So the other question that may come up on an exam, the valve used to maintain prime on a pump is sometimes called a foot valve. And basically because of where it is, based on the suction inlet line for the pump. And we'll talk more about that when we talk about pumping. But that's basically to keep the impeller flooded. But they are check valves. They allow water to flow only in one direction. And that is the key on the exam. Only allow flow in one direction.
This type of valve is called a foot valve. The sudden closing of a check valve can cause water hammer in a distribution system. To minimize hydraulic shock to the system, a special check valve called a cushion swing check may be used. Counterweights are used to slow the closing of the check valve to minimize the hydraulic transient on the system that can be created by the check valve closing too fast.
And you'll see these quite often in wastewater lift stations. They do tend to rag up, but the check valve inside will be forced open by the pump, and then turning off the pump allows the outside weight, which can be adjusted, to slowly close and allow the water column to come back without damaging either the pump or the pipe. All right. So go through the PowerPoint a little bit more. We're going to talk some more detail about altitude valves and pressure reducing valves. The video showed them as diaphragm valves within the category of globe valve, right? So we'll talk some more about those. Styles of pressure relief valves. So pressure relief valves, altitude control valves, or pressure regulating valves can all be, and typically are, control valve style, some butterfly, but we can plumb those valves in such a way that we can actually use their style of construction in order to do remote work for us, whether it's preventing a surge wave of pressure coming back against a pump and discharging it, whether it's opening to allow a reservoir to fill, closing when it's full, or allowing pressure to be regulated through a change in elevation. Air valves, basically, we have two real needs, and the exam might ask you the two main functions of an air valve. The first one we think of is taking air out of the water main. So we install them at high points because we want to keep the air, get that air out of the system. It can build up over time. And so an air valve is installed at the top part, high point of a section of the water system. And the air valves are designed that they will allow air to escape. And then once that air escapes, the float closes to prevent water from escaping. If we have a drop in the grade line, we don't want to vacuum, the float will drop because the water is escaping, air will come in. All right, I want to show you that. I think I have a cutaway of a air valve that I want to show you before. Yes. Okay, let's show you this quick 1-minute video of a cutaway of an air valve. Doesn't matter what the manufacturer is. This is a 2-inch. You can see it's all epoxy and resin, but they all function in much the same way. So it allows air to escape as the water main fills. It closes the float and seals so the line can be pressurized. If we have pockets of air building up, then the float will bounce on that buildup of air and release the air, hence the name air release. If we have a negative pressure situation, you can see the vapor coming back in, we allow air back through the grooved edges on this air valve to prevent a vacuum. There have been cases where steel water main especially, the air valves were too small or non-existent or didn't work, and a vacuum either caused by a hydrant being turned on or something hitting a fire hydrant or a water main break, and a section of main with the vacuum, steel tends to flatten and destroyed miles and miles of water main. The American Waterworks Association used to show that video quite regularly of exposing this large diameter steel that now looks like a book, you know, a folded water main that cannot be recovered. And this looks like an actual pretty good design because it's also got the hood here, because these tend to be buried directly in the ground and material can build up around it and then it won't function as it's intended to. But that's really what on an exam, they'll ask the two functions of an air valve is the release of entrained air that gets caught and built up over time, and the introduction of air when negative pressure occurs to prevent a vacuum. Okay. So backflow, obviously we do not want customer water that we've sold the customer to come back into the system. It could be polluted, it could be contaminated, it could be at a different operating pressure as well. So we install a form of a check valve over that valve. And I'll go into a little more detail on those. So we talk a little bit about gate valves. The key points are that they're for isolation when we have a legitimate need. So when we say their purpose is isolation, what it really is saying is their default position in the distribution system is open. It doesn't do us any good to have installed all these valves if they're closed. We can't get water to the customer. So default is open, but if we have to do any work, tie-ins, deal with an emergency, we can close them off to do that maintenance work. There's a large diameter valve. You can see that the larger the diameter of the gate valve, the more of that bonnet is required, because this gate must move into, retract into the bonnet to allow full diameter flow through it. Well, and when we're getting into these large diameter mains, we tend to put them on controllers, so that actuators, so that we're not turning these valves by hand. Sometimes you'll see them on these large diameters, they'll actually be designed to lie on their side. You might have seen those, in which case this stem and actuator is at a 90-degree access by the surface, and then there are little runners for the gate to roll up and down on the side of the valve. There's a cutaway, and the key parts, you know, for the exam, understand where the operating nut is. This is obviously a wheel valve as opposed to an operating nut. The O-ring basically is to prevent water escaping from the bonnet of the valve across the stem, right? The stem goes through the bonnet, through this packing gland here. And so if there's an O-ring, it will sit up here, or a packing gland, and that prevents leakage. And of course, the gate itself is the portion that basically closes or opens and restricts, isolates the flow. Very little resistance to flow, so high use in the distribution system because we don't lose the energy. Here's an example of an outside stem and yoke, and you can see by the position the valve is open. When we turn the outside stem and yoke, the stem disappears. Compared to the non-rising stem, which is this valve here. You see the operating nut? This looks like an English operating nut. It's got a different diameter. The standard American Waterworks operating nut is 50 millimeter square. The UK version is 38 millimeters. So the regular gate key will not fit. So if you allow UK variant, and of course, typical with a true UK valve is it's a right hand. Normal AWWA standard is what we would call a left hand thread. So turning clockwise closes the valve, counterclockwise opens the valve. If you're in Britain or in parts of Canada that use the UK system, and maybe you have some of those, it's a 38 millimeter operating nut, and it's right hand, so everything is backwards. So you have to be careful that you're not closing when you think you're opening, and vice versa. There was a city nearby here, and I told you, I had an issue around a fire hydrant that broke and could not close the valve because they were turning them the wrong way. So drip tight, closed. This is a resilient valve. You can see the rubber disc on that expands against the face of the valve to close it. And the other piece here is the O-ring that was mentioned on the previous slide. And that prevents leakage, right? Because you've got water pressure throughout this entire body. You don't want it escaping out the valve. And typically when valves leak, it's because either the O-ring is cracked or on older valves, they had packing glands that failed, dried up and allowed water past them. There's the bypass. I thought, there's you taking that out. Okay, so there's a bypass, and you can see we need to equalize pressure on both sides of the valve. Otherwise, you will damage the valve. Now let's talk a little bit about butterfly valves. They will ask on the exam, you know, which valve has the highest head loss, and if there's a choice between a gate valve and a butterfly valve, the butterfly valve has higher head loss because, as you can see, there is no position, open or closed, fully open or fully closed, that this valve is not in the flow path. Fully opened, it'll turn sideways, and so allow the most water through, but there is still head loss. It's not much, but compared to a gate valve, there is considerable head loss. You can see this is mounted on its side. There is a bypass construction on it to allow for that equalization of pressure across the face of the valve. But basically, also used for isolation, but it does have higher head loss. But they may ask a question about which valve is easier to open, a fully closed gate valve or a fully closed butterfly. And what they're looking for is the butterfly, because half of the surface area will always be working with water pressure, as opposed to 100% of the valve on a gate valve working against water pressure. So easier to open. However, American Water Works Association still wants a bypass on the larger diameter valves, just because, you know, you will wear out and potentially snap the valves at the higher operating pressure. So water pressure pushing on one half of the upstream side helps to force it open. Again, isolation is the key purpose, why they were built in the first place, but because of their construction and the way we can actuate the controls off the stem, and because they're much smaller and lighter on the same size diameter than a gate valve, a lot of cities have used and spec'd them for control in pump stations and pressure reducing chambers, because they can work as a throttling valve. A plug valve we've talked about, typically a corp or a main stop or a service stop. Basically, it's a quarter turn, fully open, fully closed. The shoulders of the valve prevent water flowing, so it makes it a drip tight seal. And a quarter turn opens it back up, and you can see the plug style. So when that valve is fully open, you'll actually, if you look down the gun barrel of the valve, you'll actually see the shoulders of the valve assembly. Full port simply means that when that valve is fully open, you can't see the actual valve itself, which is good. It makes it a higher efficiency. And you can see an example of that with the ball valve here. All right, globe valve commonly used, yes, so the smaller diameter globe valve would be a faucet with the wheel valve on the top and then the circular disc. You're looking at the cutaway, basically a rubber gasket on the disc itself. But notice the construction of the valve with the actual body with an inlet and outlet baffle, basically, to seat, and of course this goes around the full circumference of the valve. You're forcing the water to make a right turn, left turn, right turn, left turn to get through the valve itself. Now, across a very small distance, but there is head loss, even fully open, and we've designed it that way. So we don't want to put it at the intersection of Main and Broadway as a gate valve because there's too much head loss. If we had a whole series of valves like that, not only they're much more expensive, there'd be no water left to your last customer because of the head loss. But very suitable in other areas of the system, especially in the larger diameters like for 3, 6, and higher for controlling flow. And one of them is filling and emptying of a reservoir. The pilot assembly is spring-loaded here, and the water, as it's filling and moving through, and barely see the directional arrow, across the globe, so it's the same construction interior, allows water to flow at a higher head loss. We then plumb water to the top side of the diaphragm, and that overcomes the pressure built in on the spring, so we can either fill the reservoir, then stop it at a certain point, and then open to allow it to fill, or to drain, so that it can supply our customers. I have a cutaway scenario. Let me quickly show that to you. This is the one. Okay. So this is a cross section from one of the Clavel, or Clavel is a major supplier of control valves to distribution systems. So there's no sound, so we'll just run it through. But before I do, you'll see a flow meter. Back in the distance is our happy city, town, neighborhood. Pressure gauge on the upstream side and the downstream side. This is the globe valve. And then these are pilots that are set up, the pilot here, with strainers and orifices that allow small amounts of water to be taken from the body of the valve onto the top. And the reason I say top is there's a gasket here inside. And the area on the top of the gasket is larger than the area on the bottom of the gasket. Same gasket. And of course, we know from our hydraulics that 100 PSI on the top and 100 PSI on the bottom, because of the larger surface area, it will overcome the smaller surface area. And it controls the valve and will close or open depending on how the valve is set up. So let's just run through the animation and we'll take a look. So here's the cutaway. You can see water is moving in, the valve is closed. So it's plumbed so that as the pressure gauge is changed, you'll see the flow is at 0. This valve will start to open. So I'll let it run through once and then we'll go back over it again. But basically what this city has set it up to do is allow a lower pressure supply into a neighborhood. And if they didn't do that, the pipe in the neighborhood would be damaged. So there are times when we need more water and times when we need less. And the valve responds to that downstream demand. So watch the flow meter as this valve positions. So we'll do it again. So as the water, so they've set it up, there's say 100 PSI, 90 PSI up here. They want to keep the pressure lower because it's an elevation change. But there are times when they will need more water. People wake up, get ready for work or school, or then at the end of the day, get ready for, have dinner and then get ready for bed. So the flow meter actually, and you can connect this 2 ways, either the flow meter or the pressure gauge, and it senses what's happening through the control valve. The gasket itself is this little line here, very difficult to see, and it's wedged, it's pancaked in or sandwiched in between the seat. The seat closes, and you can see the globe valve construction style. This control valve allows water pressure on the top, and we're talking teaspoons of water, not very much, in order to push to keep the valve closed, or as the pressure drops to release this and allow flow through. And you can keep an eye on the pressure gauge, but also on the flow meter, just as the demand changes in the neighborhood. So the valve starts to modulate and fill, and they remove the pressure on the top of the gasket, which allows the valve to spring against the spring to open and then fill. And then based on the demand downstream, the valve will fluctuate or modulate, or what we often say is regulate. So the outlet's pressure stays steady, it basically smooths out, there's no hammer, and most importantly, the customers never run out of water. So the flow will change, but the gate itself, the globe valve, will modulate accordingly. And you can see the pressure, even though the flow is dropping now, the pressure is starting to build up because the higher pressure is moving and there's no demand in our neighborhood. So as the demand stops, the pressure comes up, and that's getting to a threshold where now the valve is told, again, just based on how it's plumbed, to start to close. So these become very versatile valves because they would basically be installed in a pressure regulating chamber, typically one or two. The smaller diameter pipe would open up first and allow flow through, and then as demand increases, the larger valve will open, and then in reverse order, the valves will shut down. So in an emergency, they'll open quickly to handle fire protection, but they will also allow a steady downstream pressure. I just wanted to show you a setup that's similar to how most municipal pressure regulating chambers are set up. There it is. So this is an example of a PRV. We'll go to the website without having to buy things from them. But there's an example of a PRV setup using globe valves. And you can see a couple of things here. A strainer upstream, but we have the different sizes. So they're parallel. Air valves to allow air release. And then these are gate valve style, but you can see they're outside stem and yoke style valves. And these are plumbed accordingly. So strainers in front of both, and the strainers can be blown off through the bottom or the flange removed. And it's basically a basket strainer. So you can pull the screen out and clean it if it's got dirty water. The operator here is going to put a gasket down, and it's a two-piece pre-constructed box. Everything arrives in the lower half of the box, lower it down, tie it in, pour thrust blocks, and Bob's your uncle. You can see, though, that what will happen is that when this is connected to the downstream, if there's a demand, a lot of times the smaller valve, without knowing for sure, we'll say this is a 4 and an 8, could be a 3 and a 6-inch diameter, 75 millimeter, 150. This will open first and supply the demand downstream. And because these are also check valves, it's not opening and going back up. They will be set. You can see where they've got pressure gauges ready to go, pressure gauges above and below the valve. And so as demand increases, this valve will open up further and further. And when it's topped out and opened up as full as it'll go, if it's not enough supply, the pressure gauge will start to fall, and the second valve will start to open to compensate and to fill in behind the downstream pressure. So for instance, peak demand, or maybe this valve will only open in a fire. Typically not, they would have a fire protection system in there. But you can see that gives great flexibility. Smaller valve, much easier to control for small demand and flow. And then as flow increases, perhaps in the summertime, this valve will open. And it helps, this website is about managing pressure. We'll talk about that for our O&M about making sure that we don't overpressurize our water systems. Otherwise, we shorten the life of the valves, pipe, and everything else that goes with it. So basically, that's the ins and outs of a globe valve style. Here's an example of a setup into an elevated storage facility. You can see the style of control valve here, a globe style valve with a spring-loaded pilot. The flow will come in. This is a bypass line. You notice there's not a second control valve, but it is a butterfly valve to be designed smaller diameter to be opened if this is out of service. What will happen is the reservoir will say, we need to fill. So the sensing line is connected to the pilot. The control valve will open, fill the tank. And at a certain point, the sensing line will say enough, spring will close, the diaphragm will close, and the reservoir is full. And then as the reservoir needs to drain, the sensing will come through to actually allow. This drain is actually a physical drain. I don't believe it's the line to the system, but it could be. But it allows the reservoir to be filled to preset levels, heights, elevations, and that elevation then is the information that's sent back to the control valve. So very versatile, but again, it's a globe style valve, right? They may ask you about a double acting altitude valve, and really what they're asking is it both fills and allows the tank to drain. When the distribution pressure drops below the pressure exerted by the full tank, then the distribution system information that's coming back will open up and allow that to drain into the system. So as the slide says, if it's double acting, in other words, open and closed, versus just filling, the globe valve is the same. It's just how we connect the pilot valves. This is probably the most common usage, similar to the animation that we just showed you around a globe valve, is basically to ensure that high pressure doesn't move into a lower pressure zone. That would damage our appurtenances. Our customers wouldn't be able to use the water if it's too high a pressure. It could damage their plumbing as well. So what we do is we say, all right, instead of trying to control that by closing valves or changing the size of the pipe, we need a certain amount of flow. We use the pressure control valve, the pressure reducing valve, globe style valve, to do that work. And there's an example similar to the animation. Here's our happy little city. We want lower pressure than what is going through the supply line. So we send it through a pressure reducing valve. And you can see the way they've set it up here. There's a bypass line here, normally closed, right? But it's manual. You can see the darker blue. And then we typically allow the smaller system, we set it up so they're about 5 PSI difference. And the pressure gauge below tells us is plumbed in through the pilot so that as this demand increases, this valve starts to open to fill in the need. If it's too much, then this valve will join in to supply maximum supply, including emergencies. And then as the pressure starts to climb because we've got more water going in than they're really using, then this valve will close and then the second valve will close. Okay, so that's it's all under the umbrella of globe valve. A pressure relief valve could also be a globe valve, but it has a very specific function, and that is, just as it says, to relieve excess pressure from the water line. Now, it could push it back into the system and recirculate it, or it could discharge it to the environment. The smaller diameter pressure relief valves typically sit with springs on them and dump to the environment. Control valve style typically will move that water back to the discharge side, the suction side of a pump, for instance, and just circulate it so that it can't do any damage. A control valve on a pump basically goes on the discharge side, and when we talk pumping, we'll go show you some more detail of that. but it's really designed to control pressure spikes. So pump turns on, gets the signal from the motor and the control panel to turn on. We need you to fill a reservoir, or we need you to fill up the system. We could get a spike of pressure, which could then create water hammer. So what it does is it says, no, we're going to actually start closed. Pump turns on against the closed valve and then slowly open to allow a nice steady stream into the system, and then do the reverse. Start to close when it gets the signal, hey, the pump is going to turn off in a minute, 30 seconds. We're going to start to close, because when we're talking about centrifugal pumps, that's okay to operate against a closed valve. But we don't want that water hammer getting into the system. So here's a couple of examples of the setup. You can see the pumps, the booster pumps set up, taking the water through the system. So the inlet side of the pump is the light blue. So water comes into the impeller, and the pump creates energy and sends it up, say, to a reservoir or to a community that's higher elevation. You can notice that we've got the two. Each pump has its own control valve. It has an isolation valve as well. You notice upstream there, here's a downstream of the pump is the butterfly valve, and here's a relief valve, also a control style valve. So pump is running. This valve will start shut, or this pump will run. The valve will start in the shut position and actually open up based on the information coming from the pump and also from the water that's already, don't forget, it's a pressurized system, right? So there's water pressure already here, just at a lower elevation, or lower head. So it'll fill this discharge header. The other pump may be called because it's summertime or high demand. So they're both fully open. They're high head loss, but they are fully open. Let's say something bad happens. There's a power failure and the pump's instantly shut off. Now you have this water column coming back against. This valve will start to close, but in the interim, this relief valve will be set up so that any of this extra elevation pressure head will come through this valve. It will open and discharge it. So it actually is draining it either to waste or into a tank, some sort of a retention tank, until that discharge pressure is stabilized, and then it will close. So there's no more hammer. So you'll get a hammer going of this water column coming back, and you can get then a valley, a drop. That valve will open to allow that excess head to escape, so that you don't get that high water pressure against the valves or the discharge side of the control valves. So very versatile. I showed you the cross-section of the vacuum relief. This is a very common one in this part of the world. It's not so much used anymore, but there's a local manufacturer. But you can see the float inside. So air in this chamber, the float will stay down here and the air will escape. The seat, it's tough to see, but the seat is here. So as the system fills up, say it's a brand new water main and you're filling it up, air will escape. And then as the water fills this up and there's no more air, it will lift the float and seal this. It's threaded, so you could actually put another pipe to connect it. And some cities actually brought long lengths of copper pipe and put them out to the side into the boulevard area so that they wouldn't get blocked, because if you bury this, it's not going to work as well. So then it sits up against here. There's actually a small port here where this float pushes up against. If there's a vacuum, same thing, it will drop back down, allow the air in, and then through the valve. This is connected by a 1-inch or a 2-inch short piece of pipe right into the top of the water main. And that allows the air in. So from a certification perspective, the two functions of an air vacuum relief valve are: 1, let air out, and 2, prevent a vacuum that could collapse or damage the pipe. So those are the keys there. How many need to be installed in your system is basically left up to the design engineers based on changes in elevation. If there are considerable changes of elevation, and even where a section of the water main going up a hill, if that main may be closed, there may be an air valve just below that valve, and then another one the next block up. The American Water Works Association will say, has tables that say, based on the diameter of the water main, your air valve has to be more than a 1 inch. So a 6-inch water main, having a 1-inch pipe connecting to the main into this air valve is sufficient. But by the time you get to 10, 12, and larger, that 1-inch pipe is not going to allow enough air out, or more importantly, in a vacuum situation, allow enough air in. So they will actually specify a larger size air valve based on the overall capacity volume of the bigger pipe. But for those of you writing exams, those are the two key points about air valves. Installed at the top points or high points in the line, and that they allow entrained air to escape, because air does build up in our system, and it allows or prevents a vacuum from occurring. All right, let's talk a little bit about backflow prevention devices. So we said check valves. The important thing to remember about check valve is that it prevents water from moving in more than one direction. So imagine our city supplying water to a whole variety of customers. Well, they'll do a variety of things with it. One restaurant, one laundromat, one hotel, school, hospital, all have different needs for clean water. And some may do things to that water that is not acceptable from a health perspective to have that come back into the system. So we install check valves, but we're wanting to make sure they're not just regular check valves. So if you're part of a backflow prevention program in your utility, there's certification for you to install, test, maintain those devices. We're not going to talk about that so much, the administration, except to recognize what those devices are. So it's a risk-based or hazard-based program. The higher the hazard to human health, and that's really what the American Water Works is talking about, is and local plumbing codes. If it can make someone sick, then it needs to be a highest level possible of device or assembly, and that is the reduced pressure device, which you're going to see here. We can go to a double check valve assembly or a vacuum breaker, depending on the application. But typically, when we're looking at health related, we look at RP devices. So I'm going to show you, I'm going to have a short video on the actual, yes, here's a little video on how it works. And remember, when you look at this video, what we're looking at is protecting the municipal system, the city system, the local government system from contamination. Because customers may do a variety of things. This is a bit of a sales pitch for one, but he has a schematic in it. So keep in mind that yours may look a little different, but they are all constructed, if it's an approved backflow preventer for the highest health category, so in other words, a reduced pressure principle device, they will function this way. And there may be a couple of exam questions we'll let him run through, and then we'll talk about them.
Hello, I'm Chris Hart with ARI Flow Control. In this video, we'll see how a backflow preventer works from the inside. Understanding how a backflow operates becomes much easier when you can visually see the water running through the backflow assembly. With a series of animated videos, we can illustrate the mechanical movements of the components during a back pressure and back siphonage condition. The first video will illustrate a normal flowing backflow. When pressure on the inlet side exceeds 2 psi, water flows through the sensing line in the upper chamber of the diaphragm, depressing the spring, closing the release valve. When pressure exceeds 5 psi, the first check valve opens and the zone fills. After the zone is filled, the second check opens. The gauges show the differences in pressure. When we close the inlet shutoff valve, the first check valve closes, second check valve closes, no backflow gets through. The relief valve opens. We've looked at a normal operating backflow and a shutdown process. Let's turn our attention towards valve checks under both the back pressure and back siphonage conditions. The first failure is the debris in the first check. When there's debris in the first check, pressure between the relief valve chamber and the zone equalize, and the relief valve opens. A leak from the relief valve will alarm of the problem. Second failure is back pressure in the downstream. When the pressure in the downstream is higher than the pressure upstream, second check closes, then the first check closes. In the third failure, we'll see back pressure with debris in the second check. The pressure in the downstream is higher than the pressure upstream, and there's debris in the second check. Second check closes, then the first check closes. No contamination can get through the first check. When pressure goes up in the zone, the relief valve opens and the water drains out. The next failure occurs when there's leaks in both checks. The change in zone pressure will cause the relief valve to open. The leak will warn about the problem. So after we've seen failures in a back pressure condition, now let's look at failures in a back siphonage condition. The fifth failure is back siphonage in the upstream. In this situation, the second check valve will close and leave the downstream line full. The first check valve will close and no backflow will get through. The sixth failure is showing back siphonage upstream with debris in the first check. Now the second check valve will close and leave the downstream line full. Air will get through the first check valve, back into the service line with no backflow. The last failure is back siphonage in the upstream, with both check valves leaking. During this phenomenon, the pressure loss will open the relief valve and the leak will drain through. After watching the animated videos, we hope you have a better understanding.
So basically, we're looking at two potential health issues
The change in zone pressure
in our system. And one of the most common that happens and why we need backflow prevention is that we often have to lower our grade line for doing maintenance, or there's an emergency, or for instance, a fire or a car hits a fire hydrant, something like that. And our grade line goes to zero. And you can see that on the upstream side. And the homeowner or the business owner has high pressure. Now, this is in a situation where there's debris in the check valve. But the reality is we do not want the homeowner's pressure or the business owner's pressure and then supply coming back into the city's supply. So these check valves, remember, check valve closes, only allows water to move in one direction. So under normal operation, like when we're back here, the check valves will open as we supply water to the customer, but they're independent. So not just one check valve, but two check valves, and they're not connected to each other directly. So they will open or close on their own volition based on the conditions in the pipeline. What that means too is that this space between the check valves allows for potentially contaminated water, like you saw in the one video, portion of dumping, either our system to prevent backflow or contaminants leaving, potentially contaminated water leaving the property owner's premise. So really a check valve, double check valve assembly, or in this case, a reduced pressure principle assembly, has several features. So you may be asked on a multiple choice question, what are the features of an approved backflow prevention valve? To see that the actual device is still working. And just upstream here will be isolation valves so that you can actually take it out of service. But they are designed, because this is a health hazard, the highest level hazards need to have a device that is designed to protect against both flow, i.e. back siphonage. So our system, like it shows here, 0. Our grade line has dropped, but the customer's grade line is still high because perhaps it's an elevated building. So there's now pressure coming back against the check valves. We do not want that water to come back. If you've ever worked on, say, a water meter at the property line and you turn off the city's water supply and pull the water meter, there are situations that can occur where you get hot water back into your meter box or pit. And in the wintertime, where I used to work, that felt actually pretty good. Get your hands into warm water as opposed to the freezing cold water that you normally work in. But what that means is that the property owner's water system is draining. And if you don't have a prevention method, either a check valve, double check valve, or this reduced pressure principle device, there could be a problem, a potential contamination in the customers, in the municipal system. So when we talk about maintenance of relief valves and check valves and backflow prevention devices, we're always talking about minimizing the hazard back to the utility. So this device offers the highest, the reduced pressure principle device, or RP device, offers the highest level of protection to municipal systems based on health hazards to humans. The next device down actually looks very similar to this, except there is no relief valve. It's a double check valve assembly. So it has the test cocks, it has the isolation valves, and it has 2 independent check valves. It just does not have a relief valve. Typically used when it will work the same way, but it cannot relieve potential contaminated water in this chamber. So typically used for non-health related situations. So quick example of types of valves. An air gap, you may be asked on the exam, is basically a physical break in the plumbing system. And the only question that typically gets asked about an air gap, it's not an assembly because it's actually an absence of pipe, but that the minimum size of an air gap, the physical distance, and we'll cover this off again later in a couple of weeks, is 2 times 1 inch or 2 times the pipe diameter. So imagine a 1/4 inch pipe filling a tank. There's now an air gap between the end of that 1/4 inch pipe and the tank. Well, a 1/4 inch, 2 times that 1/4 inch is only 1/2 inch. That's not enough gap. So it's basically 2 times the inlet pipe diameter, as long as it's a minimum of 1 inch. And that creates an air gap. So now you cannot have water escaping back in through back pressure or siphonage. Vacuum breaker, typically you'll see at a high point on a plumbing system, typically at a hot water tank, again to prevent a vacuum that could collapse and damage the tank. Remember, check valve allows water only in one direction. So we want to maintain prime at our trash pump through a foot valve. We want to prevent excessive discharge pressure. And most importantly, we're trying to minimize water hammer in the system, right? There you go. And water flowing in 2 directions. So what's the purpose of a bypass valve? We talked about that. Well, we're not connecting the new main. We're not increasing the flow, or has nothing to do with locating it. It's reducing the pressure across the opening and closing, right? Because of the unequal force exerted on a closed gate valve. What's the purpose of a booster valve? Well, we talked about pumping into the system, right? We want to make sure that we need that energy somewhere in the system. So we're not controlling water hammer, right? We're not necessarily controlling reservoir levels, although we can fill a reservoir, right? Whoops, that's in the wrong place. What we're really doing is maintaining adequate downstream pressure. Okay, why is it essential to ventilate a valve vault before entry? Well, this is actually a confined space entry issue. Remove the dangerous gases, right? Make it safe for workers to enter a vault. Okay, oopsie. Which of the following types of valves is best to maintain the water level in a tank? Well, the arrow is kind of giving it away. We're talking about an altitude valve. Remember that an altitude valve is typically a globe style valve. Okay, fire hydrants. Let's talk a little bit about them. Yep, we're in good time. Let me show you. I've got a quick video that I'd like to show you on the American Water Works Association has several programs around determining, the best fire hydrant to use in which condition. One of the concerns, of course, for a fire hydrant is where you live. Is there a chance of freezing or not? So we'll let the video speak. It's only a couple minutes long. So most of you have seen, worked on, or maybe perhaps installed fire hydrants. They really have one function, even though we use them for lots of different things. They're there for fire protection. Waterworks staff use them to take water samples or to clean water mains, to use as temporary water supply, which is great. That's really not why they're there, though.
Fire hydrants should be handled and installed carefully to prevent future maintenance problems or failure during operation. Inspect new hydrants when they are delivered for damage and to make sure they are as ordered and compatible with local standards and current distribution components. Check external bolts for tightness and cycle the hydrant to full open and closed positions to make sure they are working correctly. If hydrants need to be temporarily stored outside, place them with the inlets facing down to prevent moisture and materials from entering. The depth of the hydrant burial should be carefully checked to ensure the hydrant will stand the correct distance above ground. The break flange should be located about 2 inches above ground surface. Hydrant spacing typically ranges between 300 and 600 feet. They should be located far enough back from a roadway to minimize the danger of being struck by a vehicle, a minimum of 2 feet from the face of a curb. The 4-inch pumper outlet nozzle should face the street or road for easy access and be at least 18 inches above the ground line to allow for the attachment of hoses and operation of a hydrant wrench. Fire hydrants must be set on a firm footing. The hydrant must also be securely blocked or restrained from movement, since the force against it will be tremendous if the valve is closed quickly. If possible, the excavation should not disturb the earth directly behind the footpiece. Newly poured concrete or concrete blocks can be placed in the void to help block the hydrant. If the ground behind the hydrant is too soft for blocking, rods can be installed to secure it. Mechanical joints are also becoming more common in hydrant installations. Make sure there's ample drainage for dry barrel hydrants by providing a drainage pit if necessary. Place at least 1/3 of a yard of clean stone around the hydrant base. The stone should cover the drain outlets to a depth of at least 1 foot on all sides.
So the question for you is, in your water systems, do you use dry barrel fire hydrants that drain to prevent freezing? If you use a wet barrel fire hydrant, then that would not apply because you cannot drain the fire hydrant at this point. The standpipe is full all the way up to the bonnet assembly. So we'll talk about that in a minute. But basically what they're saying here is if you have a fear of freezing, where most, in North America, most hydrants have that opportunity, then there will be a drain either at this location for a compression style hydrant or at the base of the boot, the hydrant boot, on a slide gate style. It needs to drain, otherwise the hydrant will be damaged in the winter.
Take care to not block the drain holes during installation and protect the drainage pit from infiltration of soil by covering it with a waterproof material or possibly a filter fabric that keeps the drainage pit rock and soil in place but allows water to drain away from the hydrant. Many water systems now color code their hydrants to indicate the flow capacity. Here is the color code as suggested by AWWA and the National Fire Protection Association. Record keeping is an essential part of a successful maintenance program. Make, model, depth of burial, specific location, auxiliary valve info, and flow performance at the time of installation should all be noted. An entry should then be recorded each time the hydrant is tested, inspected, and repaired. For more detailed information on work.
So a couple of things for the exam. It's important to know for exam purposes, the style of hydrant, right? We know that they're essential for fire protection, typically with between 100 and 150 meters between hydrants is standard, but that depends on the city's ordinances. Obviously, it needs to be clear and unobstructed. You've probably all seen pictures on the internet of fire departments having to smash car windows to get to the fire hydrant and then drag the hose through. As I said, we've used them for lots of different purposes in our water system maintenance, but really they're there for fire protection. So as such, a lot of our standards about height off the ground and clearance from the curb are around access for firefighters. Typically, a fire hydrant is basically serviced with a 6-inch, 150 millimeter nipple or hydrant stub or leg off the water main with its own control valve, basically a gate valve that in its default position should be open, otherwise the fire hydrant will not work. The valve stays open, and then the firefighters or the operator control the hydrant through the operating nut at the top of the hydrant. For the exam purposes, the two types of hydrants are dry barrel or wet barrel. So if freezing is not an issue, sometimes they're called California hydrants, but basically a wet barrel hydrant allows water always under pressure right to the operating nut, to the head of the hydrant. So there is no drain. Whereas a dry barrel hydrant, where there's freezing, those hydrants will have a drain. So when it's installed, it needs to have coarse material around it to allow that hydrant, the water to drain after the hydrant's been used or serviced. Within the style of hydrants too, the two styles basically are compression hydrants or slide gate hydrants. There will be a question on the exam, which hydrant is easier to operate or uses line pressure to assist the operator in closing. And the compression hydrant, like a compression style with a gate valve, basically allows water pressure as the valve is closing to help seat and shut the valve. Breakaway flanges are typically allow the hydrant to tear off with the stem and allow the hydrant to not be damaged. The other issue around that is if the stem is connected to the seat at the base, could be a meter deep, it could be 4 meters deep in some places because of freezing. If that breakaway flange doesn't happen, it could damage the water main, at the base. So here's a cutaway of a compression style dry barrel fire hydrant. And the important thing here is to note is that the actual drain is, I can't see it too well, but it's here. So the water main is under pressure. The fire hydrant is under pressure to this seat on the valve. And it's like a full port valve, because when the hydrant is opened, it opens against water pressure and the stem turns and forces the seat down to the base. So now we have basically a full port of water that can flow out of either the pumper or the side ports. When the valve closes, it returns back up and closes against the seat, which then means this will be pressurized. So this portion of the hydrant barrel needs to drain. So that's why the drain is here. This is the breakaway flange coupling so that the hydrant, if it's struck by a vehicle, will knock away and not damage this. This material will still stay shut. In fact, we had a homeowner in his truck bring us this portion of a fire hydrant, said, I found it in the ditch, and it had been there for over a year. So the issue was, why hadn't the crews gone to inspect it? But there was just a hole in the ground. There was no water because the compression valve closed against the seat and the broken stem just basically sat there in the bottom of the ditch. So not good for a few reasons. The hydrant is operated from the operating nut at the top here. And because it's a dry barrel hydrant, it's the operation of this top portion, which has got some lubricant in it here, and then the O-rings to prevent water leakage. Basically, it's operating it remotely, right? The control function of the hydrant is here. Another portions of it. So basically allowing, and so the key here too is that because the drain is here and not at the bottom, when this hydrant is installed, the proper base and some drainage material around the base of around the drip valve allows that hydrant to drain in the winter. And you can feel operators that are operating this type of hydrant, when they are shutting the hydrant down and closing it, the hydrant port caps will be open. You'll be able to feel the suction as the air drains through the hydrant itself. Okay, let's go to that video I wanted to show you. Okay, where are we for time? What's the time? I do want to bring up the answer sheet from last week too, though, before we finish. Yeah, here's a short vid. All right, where are we? There it is. So this is a compression style hydrant. You can see the cutaway. So there's the seat right here. So this will all be under pressure. You can see the lugs on the side so that the hydrant can be rodded into the water main and the stub. This is the seat itself, and operating it drops the seat down. And so it's got the full flow. And as it's closing, you can see that when the comment, yes, it closes with the help of water pressure, because the water pressure will move up across the face. And as this is retreating back into its seat, water pressure will help close it. This is the breakaway connection. So we call it a frangible connection. You can see how it's been cast here. And then this two-piece or two-part coupling. So a vehicle striking the hydrant above grade will snap it off here and then not damage the part that actually holds back the water pressure. You can see the operating nut on and the wrench, but they're the O-rings that prevent water from leaking through the open portion of the hydrant and up through the operating nut. You can actually see the valve moving down towards the base, and then the travel nut here stops it, but allows the full flow through to go through the void created after the seat has been pushed down. Oops. So, the other piece that I wanted to remind you is that basically we're looking at this also is a dry barrel, and it's a compression style fire hydrant. Same features as a slide gate hydrant. They do have some breakaway flanges. The slide gate is a much older style, but both allow for use in colder climates so that if need be, you know, they don't freeze up and they can be properly drained. The two other pieces about, we'll talk more about hydrant maintenance in the O&M section of the program. Terminal City was one of the big suppliers of fire hydrants. I just wanted to show you the cutaway that they had. This might be the better picture I will share with you. Nope, that's the wrong one. Bear with me. Here we go. Okay, that's the one. So let me just share this with you. So a slide 8 fire hydrant, if they ask on the exam, you can see the difference between the compression fire hydrant that was just on the screen and a slide gate. So just like a non-rising stem, as you operate the hydrant from the operating nut at the top, this gate, very much like the gate in the gate valve, will move up and down, allowing flow past. This is where the drain is. You can see on the base now, as opposed to on the compression hydrant, where the drain is up at the seat, right? The compression hydrant has its seat at this portion, and then allows a slightly higher volume of flow through, and then water pressure will help it close. Whereas you can imagine, this is under full pressure. The hydrant is pulling the slide as you operate to open up the fire hydrant. The slide gate moves up. The drip valve closes because you don't want the water going out the bottom while the hydrant is being operated. And then flow goes up through the base into the body and out the port. When you're shutting the hydrant down, the operating nut doesn't change its elevation, right? It stays the same. The gate, the screw turns, the gate spins through and then seals. And actually this little triangle here is actually a wedge, helps push it, the face of the gate valve, up against the face of the hydrant boot, and then holds back the water pressure. So it's actually a wedge nut, but it actually closes against water pressure, whereas the compression hydrant closes with water pressure. This we may not see too well, but just as a summary, the two main types of questions on the exam tend to be around closing with or without water pressure. And there you can see a good cutaway, same company actually, a good cutaway. There's the compression style. The drain is up here, opening against the water pressure, closing with the water pressure, right? So the drain is in a different location, whereas on the previous one, the drain is below. But both these styles of hydrants are what we call dry barrel. One is compression, the other is slide gate. And the dry barrel is always used in areas where there is a threat of frost or freezing. Okay. We're just about done, I think. Then we'll just do the review questions from yesterday and then set you free. So, which type of hydrant is hidden from public view? We didn't really talk about that, but what we're really talking about here is a flush hydrant. And you'll see them, some of them, and they're not talking about flushing water mains, but flush mounted. So it's actually a plate in the road, and then you or sidewalk, and you access the hydrant from below. And it's really a fire protection system for private property. Which hydrant offers the least amount of head loss? So between, really, we've got two choices. It's actually these arrows are in the wrong place, but it's the compression hydrant. Slide gate, because it actually sits against that seat, like I showed you, is a little more head loss. How should a hydrant be properly operated? So when we talk about flushing in the next little while, we will talk about making sure that when we're moving high volumes of water through the water system and using hydrants to do that, it's really critical that we don't create water hammer, right? We open the hydrant slowly. We have to open it fully because we don't want that drip valve, if it's a dry barrel hydrant, to be impacted, but it's really critical to close the hydrant slowly. right? We talked about this. Dry barrel hydrants are used in which type of environment? Like, not hot. It should be aiming at freezing, right? We protect against frost, right? We want the hydrant barrel to drain so that it doesn't freeze. All right, which hydrant type has no main valve, but each nozzle has a separate valve? Well, that's one of the advantages of living in a place where it doesn't freeze. The wet barrel hydrant allows water pressure right to the operating nut, and each valve can be separately operated. Okay, so that's the piece on hydrant valves. I took the meter part out because there's lots of different types of meters, so that gets its own session next week. Let us, though, just quickly bring you, let's see, the answers. Nope, not that one. The answers to the questions from last week, week 5. I will send you these through Ignatius. I will send you the PDF as well. But while we're here, may as well, got a couple minutes, we'll take a quick look at the questions from last, and then, as I say, we will send you on your way. So, nope, that's this week's questions. There we go. All right, so why is it important to clean reservoirs? Obviously to maintain water quality. And when we talk O&M in the next couple of weeks, we'll talk about how often you should clean a reservoir and what methods to do that in order to ensure that it's, it lasts a long time. Disease-causing bacteria, pathogenic. Remember we talked about the difference between 1.20 milligrams per liter is the same as 1.2 parts per million. Okay. On the pH scale, liquid with a pH of 4.5 is acidic. 8.0 is basic. Alkaline is use basic. Alkaline will not be an option on the exam. Sodium hypochlorite.
Sorry,
Go ahead.
but I'm not seeing your screen.
Oh, it says I'm sharing it, but
Yeah, I'm seeing it. Funny.
It showed a different one, not what you're reading.
oh, maybe you're okay. Hang on a sec. Let me close it. I'll stop it. And,
Okay.
I'll stop it and reshare it.
Yeah, I think yes, you're right.
Okay. Let me try it again, just to make sure you're looking at the right one. How's that? Assignment 5 answers. Are you seeing that?
Yes.
Correct.
Cool. Okay. So 4.5 acidic, 8 basic. Typically sodium hypochlorite, there's obviously a range, but it's nominally a 12% strength, whereas household bleach is typically 4 to 5 to 6%. Remember, on the multiple choice certification exam, you're not going to have any fill in the blanks. We did it make it a little tougher to have to find them, but you will have a choice of the right answer in here. Advantages of using ultraviolet for disinfection. There are a couple. Best answer, no disinfection byproducts. It's also highly effective against Giardia and Cryptosporidium, not just coliform. Disadvantages, though, water that's higher turbidity, so water that's typically surface water supplies that have seasonal freshets and high cloudy episodes, intrusion events, and so on, not great. And remember, ultraviolet does not provide a residual. So typically when used, cities will actually add chlorine afterwards. Breakpoint chlorination, remember the process of disinfection. We reach the point when any additional chlorine adding to the water column after we've met the demand, now we are creating a residual. So it is actually a point on the chlorination disinfection curve where at that point, at that break point, demand is met or satisfied. So we don't have to add more, but when we do add more, it creates a residual that we can now measure. And a math question, if dosage is 2.0 milligrams per liter, the residual is 0.8 milligrams per liter. For certification purposes, we're not doing anything with that 20 minutes of contact time in terms of calculation. Really, it's just dosage equals demand plus residual. Therefore, residual, we have to subtract demand from dosage, and the other way around. Demand, to calculate demand, we subtract the residual from the dosage. Dosage is always the total, sum total of the amount of chlorine added. It is either demand used by organics or any material in the water column. The result afterwards is what we call the residual, right? And remember, we'll talk about this more under review. You will always be given 2 out of the 3 values in order to calculate the correct answer. And because it's multiple choice, one of those answers is correct. So if you can do the math, you'll find that answer there. So I'll send you these as well. I'll send them through Ignatius. The other document I just closed is the questions for today based on our discussion around valves and hydrants. There's more coming next week on water meters, and then the plan is to start talking about operation and maintenance and highlight those operational areas that tend to be subject to questions on, that will come up in your certification exam. And some of these processes you'll be already using, some of the procedures you'll be following already, some not. It all depends on budgets and age of the system and so on. So we'll cover off some more of that in the weeks to come. And I think that should do it for today.
Yeah, thank you, Mike. That was very good. Before we leave, I think Valerie wanted us to do a screenshot.
Oh, right. Yes.
Can
Thank
you
you.
do that if you show your videos so that we can get that shot for her?
Show the video? Oh, yeah.
No, I'm asking the other participants if they want to share their.
Perfect.
Show themselves.
Busted.
It doesn't seem they're keen on that.
There they are.
Yeah, come on, pop up.
Right, because Valerie's doing that report, isn't she?
Yeah, she's working on some report and she wanted everyone to share the videos. So we can take a video, a screenshot of everyone. Let's see, but now I can't get. No. Who's missing? Well, some people are shy. They don't want to show themselves. What about Rashford and Nicole and Burnell?
Just have to put down their beer.
Ezekiel. Okay.
Nice.
I think we're missing Ken and Joseph.
There he is.
Bowen. Oh, we have quite a few there. Mr. DuPlessis. I can't get Mr. DuPlessis. He seemed to. All right. All right. Well, you go ahead, Mike.
Okay. Got it.
All right, great. All right, then, as we indicated for those of you who joined us late, was that we are going to, contrary to what I said last week, we are going to have the exams on from the window from the 16th to the 19th of April. And our final tutorial is going to be on the 14th of April, when both Mikes will do a revision sessions on treatment and distribution, respectively. So
Great.
thank you again for joining. And thank you, Mike.
Okay. We'll see you next week at same time.
Next week, same time. And for some of you who may be joining us in a few minutes time for our CAWASA Wednesday webinars, which is going to be on chlorine part 2 with the Chlorine Institute. So see you in a bit. Bye.
Thank you.
Thank you.